Hello, everyone. This is our ECE6775 final project, the Julia set calculation accelerator. First, we will give a brief introduction on the Julia set. The Julia set is a famous mathematical construct that relates to fractal geometry. The set is formed by identifying which complex numbers, when iterated through a function, remain bounded and which escape to infinity. The Julia set is particularly famous because of the visually stunning image that it produces. Next, we're going to show the iterative function that we pass each coordinate through. The function is in the form f of z is equal to z squared plus c, where z is the complex number. In our case, we split the function into two parts, one for the real part and one for the imaginary part to make it easier to implement. We then iterate on each coordinate until either the divergence condition is met or the maximum number of iterations is reached. Our project goal is straightforward. We want to design hardware using HLS that produces the Julia set. The design will output a set of iteration values, which can later be mapped to colors. And using a Python script, we can plot the colors and hope to obtain our own version of the Julia set.
We will now be talking about one of our key designs, our dispatching unit. What the dispatch unit does is that it adds parallelism to our high-level synthesis program, where multiple pixels can be calculated at the same time. Our dispatch unit consists of a dispatch function, which kind of acts as a load balancer that assigns each task that we have to perform into each processing element, and then merge them all together. Our data within the dispatch unit is communicated via first in, first out flows, and how each pixel is assigned to their corresponding processing element is through round robin scheduling, where we would iterate through each processing element and assign them the next pixel that we have to calculate. One variable that we have in our design is the size of the image, since it determines how many pixels that we have to calculate in our program. Some of the challenges that we face while designing our dispatch unit is how to determine our first in, first out queue size. We found out that when we set it too low, such as like single digit integers, that sometimes will cause deadlocks because our queue is too shallow. However, when we try to increase our first in, first out queue size by too much, it also violates our resource constraints. Our proposed solution for it was to implement non-blocking reads in our merge function and checking the loop for valid reads.
So for testing, we first wrote a software program in MATLAB that generated the image of a Julia set. And then we wrote our own program in C++, and checked that the output image is the same as the output image as the MATLAB image. Using the software program, we developed our hardware design, the one with the dispatch design. And we compared the dispatch hardware design results to the C++ software program results, once again, by comparing the output and the image file. And then we made sure that our hardware design could pass both HLS, CSIM, and COSIM, and that it runs on the Z-board. And so for results, both of our software and hardware designs output number of iterations for each pixel to a very large text file. And we then wrote a Python script that would read the each number of iteration in the output text file, and from there assign each range of iterations to a color, and then produce an image like the one shown on the slides. And just for a quick demo, we'll show that our design works on the Z-board FPGA. So here I'm already logged into one of the Z-board servers, and the bitstream is already mounted to the SD card. So we'll just use make FPGA to run it. So make FPGA both compiles our design and runs it on the Z-board. Okay, and then from here we're gonna SCP the results back to the EC Linux server. And so the results is in our script, it's automatically put into the output folder. So now the dataflow output.txt, which contains the number of iteration, is on the EC Linux folder, and I'm going to download it so that it is downloaded to my local laptop just so we can produce the image. And then my local terminal, I will display. Let me share the screen for the image. So here is the image that is produced by the Python file. You can see it does show a Julia set. And now going back to our evaluation results.
So the evaluation results shows a trend of iterator latency and resource utilization for different numbers of P's. As the number of P's increased from 1 to 32, there is a significant reduction in both minimum and maximum iterator latency, which indicates increased computational efficiency. The resource utilization also shows proportional increase with number of P's. The latency shows a substantial decrease in growing parallelism. Comparing to baseline with 1P, we can see the speed up is 2 with 2Ps, 4 with 4Ps, and 8 with 8Ps. With 32Ps, the speed up reaches maximum of 38, showing the significant acceleration of computational tasks. However, FPGA execution time shows a slight increase. The graph shows the increasing trend of resource utilizations as the number of processing elements increase. It shows that the usage of lookup table, LUT, and flip-flop, FF, increase rapidly as we use more Ps. To summarize, this evaluation highlights the trade-off between computational speed and resource utilization. Thank you.